For this video, we're looking at the first derivative test graphically. So the first derivative test is a test to find a max or a min of a graph, a relative max or a min. So what you should already know is that relative extrema will happen when the first derivative is 0. So let's say it's f prime of c equals 0, or f prime of c is undefined. Okay, and c would be a critical number. So if this is the graph of our first derivative of f, then we know that we have two critical numbers here. There are two places where the first derivative is 0. One of them is at -1, and the other one is at 1, 2, 3, 4, 5. Okay, so we have two critical numbers. We could have a max or a min at either one of those. Well, this should be fairly repetitive for you. We've done this before. If you look at this graph right here of f prime of x, I know that from negative infinity up to -1 that f prime of x is less than 0. It's below the x-axis, all the way from the left up to this point. What that means is that f of x is decreasing on that interval. Because I know that f prime is the slope of f. If you look from -1 to 5, my f prime of x is above the x-axis, it's greater than 0. So I could say from -1 to 5, f prime of x is greater than 0, which means that the original graph, f of x, is increasing on that interval. On my last interval, it's to the right of 5, so I could say from 5 to infinity, f prime of x is again less than 0. It's below the x-axis. So I know that f of x is decreasing. Now, if I think about a relative max or min, so let's think about our original function. So we're going to call it f of x, some random f of x. But if I draw something that looks like a relative max, it's right here. My relative max is right there because it's the highest point in an open interval. And I look at its slope, I know that my graph was going up, so my slope was positive before the critical number, before the max, and afterwards the graph is decreasing going down, so my slope is negative. So my graph was increasing, then decreasing. This would be the relative max. For a relative min of f of x, a min would be right here. It's the lowest point in an open interval. My graph was decreasing before it, so the slope was negative, and increasing after it, so the slope was positive. A negative derivative to a positive derivative, so I have a relative min. These give me my justifications for a relative max and a min. For a relative max, you can see the slope change from positive to negative, so I would say f prime of x changes from positive to negative. For my min, f prime of x changes from negative to positive. So coming up to this graph, my derivative was negative here and positive here. My original function was decreasing and then increasing. So x equals -1 is a relative min. And if I was asked to justify it, I would say f prime of x changed from negative to positive at x equals -1. Over here, f prime of x changes from positive to negative. My graph was increasing before this point and decreasing after. So x equals 5 is a relative max. And again, if I was asked to justify it, I would use this justification. F prime of x changes from positive to negative at x equals 5. And this test right there with these justifications is the first derivative test. You are using the first derivative test to see if we have relative mins or maxes. Now, it's important to note here that if your derivative is 0, that's not enough. Because if you imagine that my graph came in, hit 0 at -3, and then went back up, this was the graph of my derivative. -3 is a critical point. It's a critical number because f prime of -3 equals 0, and that's fine. However, f prime of x did not change from positive to negative or negative to positive. In fact, it went from positive to positive. So my original graph was increasing before it flattened out and increasing after it flattened out. So this is actually just a point of inflection. But that's a look at the first derivative test graphically.